Good day, sir. We are here to discuss the topic of set operations. My name is John Imantisbi Pulido.
I'm Debbie Ansulang.
Nornin Semblante.
Robert Candilang.
And we are the Group 2.
Sets operations. Our discussions explores the fundamental concept or sets operations and their practical applications. Introduction to sets. Sets are collections of distinct objects also known as elements. Sets can be described using curly braces or by listing their elements separated by commas. For example, set A, B, and C represents a set with three elements A, B, and C. Sets can be finite, containing a fixed number of elements, or infinite, containing an unlimited number of elements. Sets play a crucial role in various fields include mathematics, computer science, and statistics. Sets operations are fundamental action we can perform on sets, collection, and distinct objects. These operations include union, intersections, difference, and complement. Let A and B be sets. The union of the sets A and B, denoted by A union B, is the set that contains those elements that are either in A or in B, or in both. The Venn diagram shown in Figure 1 represents the union of sets A and B. The area that represents A union B is the shaded area within either the circle representing A or the circle representing B. So we will give some example of the union of the sets. So here's example number 1. The union of the sets 1, 3, 5 and set 1, 2, 3 is the set 1, 2, 3, 5. That is set 1, 3, 5 union of set 1, 2, 3 is equals to set 1, 2, 3, 5. So let's break down the step-by-step solution of this example number 1. So this is a union of two sets. Sets involves set A is equals to set 1, 3, 5, set B is equals to set 1, 2, 3. So the operation that we use here is the union. So the definition here is the union of two sets A and B denoted by A union B includes all unique elements that are in either set A, set B, or in both. So step-by-step explanation here. So step 1. Identified elements in each set. Set A contains elements set 1, 3, 5. So set B contains elements set 1, 2, 3. So the step number 2 is combine all unique elements from both sets. So list all elements from set A, which is set 1, 3, 5. So let's elements from set B, which is set 1, 2, 3. So now step number 3. So merge the elements and removing duplicates. Combining the elements, we get set 1, 3, 5, 1, 2, 3. So remove duplicates to get the unique elements, which is set 1, 2, 3, 5. So the results here is the union of sets A and B is A union B is equals to set 1, 2, 3, 5. In the visual representation using a Venn diagram, imagine two overlapping circles. One circle represents set A and the other circle represents set B. The union, the combined area of both circles includes all the numbers in either circles, which is set 1, 2, 3, 5. The conclusions here in these examples, the union operation combines the elements from both sets without duplicates, resulting in set 1, 2, 3, 5. Let A and B sets the intersections of the sets A and B, denoted by A intersects B, is the containing those elements in both A and B. Elements X belongs to the intersection of set A and B if and only if X belongs to A and X belongs to B. This tells us that A union B is equals to set X such that X elements A and X elements B. The Venn diagram shown in figure 2 represents the intersection of two sets A and B. The shaded area that is within both the circles representing the set A and B is the area that represents the intersection of A and B. So we give some example of intersection of sets. So here's the example number 3. The intersection of the sets 1, 3, 5 and the set 1, 2, 3 is the set 1, 3. That is, set 1, 3, 5 intersect set 1, 2, 3 is equals to set 1, 3. So let's break down the step-by-step solution of this example number 3. Example number 3 is an intersection of two sets. Sets involved. Set A is equals to set 1, 3, 5. Set B is equals to set 1, 2, 3. The operation that we use here is the operations intersections. So the definition, the intersection of two sets A and B denoted by A intersects B includes only the elements that are common to both sets. So here's the step-by-step explanation. Now, step number 1. Identify the elements in each set. Set A contains elements 1, 3, 5. Set B contains elements 1, 2, 3. So the second step is to determine common elements. So compare elements from both sets to find common ones. So common elements between sets A and set B is 1, 3. So the result here, the intersections of sets A and B is A intersects B is equals to set 1, 3. The visual representation using a Venn diagram, imagine two overlapping circles. One circle represents set A and the other represents set B. The area where the two circles overlap contains the elements common to both sets, which is 1 and 3. Conclusion in this example, the intersections operations identifies the elements 1 and 3 as the common elements in both sets A and B, resulting in sets 1, 3.
Two sets are called disjoint if their intersection is the empty set. Example, let A equals set 1, 3, 5, 7, 9 and B equals set 2, 4, 6, 8, 10 because A intersect B equals empty set. A and B are disjoint. We are often interested in finding the cardinality of a union of two finite sets A and B. Note that A plus B counts each element that is in A but not in B, or in B but not in A exactly once, and each element that is in both A and B exactly twice. Thus, if the number of the elements that are in both A and B is subtracted from A plus B, elements in A intersect B will be counted only once. Hence, A union B equals A plus B minus A intersect B. The generalization of this result to unions of an arbitrary numbers of sets is called the principle of inclusion-exclusion. The principle of inclusion-exclusion is an important technique used in the enumeration. We will discuss this principle and other counting techniques in details in chapter 6 and 8. The intersection of disjoint sets are set A equals a set of 1, 3, 5, 7, 9 and set B equals 2, 4, 6, 8, 10. So the operation here is intersection or not one. So the intersection of two sets A and B denoted by A intersection B includes only the elements that are common to both sets. Here are the step-by-step explanation. First one, identify elements in each set. So, muna ito contain ang A of 1, 3, 5, 7, 9, while ang B contains 2, 4, 6, 8, 10. Step 2, determine common elements. Compare elements from both sets to find common ones. Since there are no common elements between set A and set B, the intersection is an empty set. So, the result is the intersection of sets A and B is A intersect B equals empty set. It's a visual representation using a Venn diagram. Imagine two non-overlapping circles. One circle represents set A and the other represents set B. Since there is no overlapping area between the circles, it shows that there are no common elements. So, the conclusion in this example, the intersection operation identifies that there are no elements common to both sets and B, resulting in an empty set. A and B sets. The difference of A and B, denoted by A minus B, is the set containing those elements that are in A but not in B. The difference of A and B is called the complement of B with respect to A. So here's the remark. The difference of sets A and B is sometimes denoted by A/B. An element X belongs to the difference of A and B if and only if X elements of A and X not element of B. This tells us that A difference of B equals set of X such that elements of A intersect X, not elements of B. The Venn diagram shows in the figure 3 represents the difference of the sets A and B. The shaded area inside the circle that represents A and outside the circle that represents B is the area that represents A difference B. We give some examples of differences of sets. Example: the difference of set 1, 3, 5 and set 1, 2, 3 is the set 5, that is set 1, 3, 5 minus set 1, 2, 3 equals set 5. This is different from the difference of set 1, 2, 3 and set 1, 3, 5, which is the set 2. So let us break down the example step by step to explain it clearly. So here, the difference of set 1, 3, 5 and set 1, 2, 3 is the set 5. That is set 1, 3, 5. The difference set of 1, 2, 3 equals 5. So the concept here, the example demonstrates the concept of set difference denoted by A minus B. The set difference A consists of elements that are in set A but not in set B. The first step is the concept. The example demonstrates the concept of set difference denoted by A minus B. The set difference A consists of elements that are in set A but not in set B. The second step is elements in sets, which is identify the elements in each set. Set A has the set 1, 3, 5, set B 1, 2, 3. The third step is finding the difference. Compare the elements of set A with set B. 1 is in both sets, so it is excluded from the difference. 3 is also in both sets, so it is excluded from the difference. 5 is in set A but not in set B, so it is included in the difference. The fourth step is the result. The resulting set is 5, as it is the only element in set A that is not in set B. The fifth and final step is the explanation. Therefore, the difference 1, 3, 5 minus 1, 2, 3 equals 5. Here is an additional context. The set difference A can be visualized using a Venn diagram, where the shaded area represents the elements of set A that are not in set B. It's important to note that the order of the sets matters in set difference, which is the set 1, 3, 5 difference set of 1, 2, 3 equals 5. And the set of 1, 2, 3 difference of the set 1, 3, 5 equals 2. And the set of 1, 2, 3 difference of the set 1, 3, 5 equals 2. Let U be the universal set. The complement of the set A, denoted by A, is the complement of A with respect to U. Therefore, the complement of the set A is U different A. Here's the remark. The definition of the complement of A depends on a particular universal set U. This definition makes sense for any superset U and A. If we want to identify the universal set U, we would write the complement of A with respect to the set U. An element belongs to A if and only if X is not an element of A. This tells us that intersect equals the set of X elements of U such that X is not an element of A. In figure 4, the shaded part or the shaded area outside the circle represents A is the area representing A. We give some examples of the complement of a set. For example, let A equals set of A, E, I, O, U, where the universal set is the set of letters of the English alphabet. Then intersect equals the set of B, C, D, F, G, H, J, K, L, M, N, P, Q, R, S, T, V, W, X, Y, Z. So here's the explanation of set complement. In this example, we are exploring the concept of the complement of a set within the realm of set theory. Our task is to determine the complement of a given set A with respect to the universal set U. The universal set, or the U, in this context is defined as the set of all letters in the English alphabet. The set A is given as A equals the set A, E, I, O, U. These are the vowels in the English alphabet. So finding the complement, to find the complement of A denoted as A, we need to identify all elements in the universal set U that are not in the set A. In other words, A consists of all the consonants in the English alphabet. Here's the calculation. The complement A is A set of B, C, D, F, G, H, J, K, L, M, N, P, Q, R, S, T, V, W, X, Y, and Z. So the conclusion here, this example demonstrates the concept of the set complement, where the complement of a set A includes all elements in the universal set U that are not in A. So I would like to give you a visual representation. So imagine a diagram where the set A is represented by a circle containing the vowels, and the universal set U is a larger circle encompassing all letters of the alphabet. The area outside the circle representing A, but within the universal set U represent the complement A. I would like to move forward in a new aspect, which is the set identities. The image discusses the identities of unions, intersections, and complements of sets. It mentions that several identities will be proven using different methods and highlights the similarities between set identities and logical equivalence. This topic is crucial for understanding how different set operations relate to each other and how they can be used to solve various problems in set theory. Here's a table. So as you can see, there are two columns that entitled identity and its name. In the first column, which is entitled the identity loss, it shows that A intersects U equals A, and A union empty set equals A. In the second column, which is named domination loss, we can see that A union of U equals U, and A intersect empty set equals empty set. In the following column, which is named idempotent loss, A union of A equals A, and A intersect A equals A. The following column is complementation law. we can see that A is inside a parenthesis and is equals to A. The following column is commutative loss. We can see that A union of B equals B union of A, and A intersect B equals B intersect A. The following column, which is named associative loss, in the following column you can see that it's named associative loss. Here we can see that A union of B and the union of C is equals to A union of B and the union of C. The next one is the A intersect B and intersect with C equals A intersect B and intersect with C. The following column we can see that it is named distributive loss. And we can see here its identity is A union of B and intersect with C is equals to A union with B and intersect with A and union of C, and A intersect with B and the union of C and is equals to A intersect with B and union of A and intersect with C. The next column is De Morgan's law. Here we can see that A intersect with B is equals to A union of B, and they intersect with A is the union of B is equals to A and intersect with. And the following column is absorption loss. Here you can see that A union of A is intersect with B and is equals to A, and A intersect with A and is the union of B is equals to A. The last column is the complement loss. Here you can see that it's A, the union of A is equals to U, and is A intersect with A is equals to empty set.
Atomic sets are the basic components used to create more complex set combination. Venn diagrams are useful for visualizing set identities, especially with 2 or more atomic sets. However, with 4 or more sets, Venn diagrams become complex, requiring ellipses for accurate representation. While Venn diagram provides informal proofs, formal proofs are necessary, often involving showing that each set is a subset of the other. As demonstrated by De Morgan's laws, the text emphasizes the need for formal method to prove set equality. Generalized union and intersection. The concept of generalized union and intersection in set theory is crucial for understanding how sets interact. According to the associative laws, the order of operation in unions and intersection is clear and ambiguous. Let A equals the set 0, 2, 4, 6, 8 and B the set 0, 1, 2, 3, 4 and C equals the set 0, 3, 6, 9. What are the A union B union C and the A intersect B intersect C? Solution. The set A union B union C contains those elements in at least one of A, B, and C. Hence, A union B union C equals the set 0, 1, 2, 3, 4, 6, 8, 9. The set A intersect B intersect C contains those elements in all three of A, B, and C. Thus, A intersect B intersect C equals 0 set. In figure 5 image shows the union and intersection of A, B, and C. The shaded part is a union B and union C in A, and B is the part of the shaded is the A intersects B intersects C. We can also consider unions and intersection of an arbitrary number of sets. We introduce these definitions. The union of collection of set is the set that contains those elements that are members of the at least one set in the collection. We use the notation A1 union A2 union 2 union AN equals union and bring down IN 1 AI to denote the union of the set A1 A2 to AN. The intersection of collection of set is the set that contains those elements that are the members of all the set in the collection. We use the notation A1 intersect A2 intersect to intersect AN equals intersect NI bring down IN1 AI to denote the intersection of a set A1, A2, and to AN.
Computer representation of sets. Storing elements in an unordered manner makes sets operations like union, intersection, and difference computationally expensive. This is because this operation involves searching for elements within the sets. A solution: bit string representation. Ordered universal set. To address this, we assume a finite universal set union with an arbitrary ordering of its elements. Set A.G. A1, A2 AN. Bit string encoding. Each subset A of union as represented by a bit string of length n. The ith bit in the string is 1 if the element AI belongs to A and 0 otherwise. Benefits of bit string representation. Efficient set operations. This method enables fast computation of set operations. For example, union. Bitwise OR of the bit strings representing the sets. Intersection. Bitwise AND of the bit strings. Difference. Bitwise AND of the first sets bit string with a bitwise NOT of the second set's bit string. For example, if union equals is a set of 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and the ordering is natural set 1, 2, dot, 10, then the subset of odd integers would be represented. Then the subset of the odd integers would be represented as 1 0 1 0 1 0 1 0 1 0. In essence, this method provides a compact and efficient way to represent sets in computers, making set operations computationally feasible. Multisets. Definition. A multiset is an unordered collection of elements where an element can occur. Unlike sets, the number of occurrences of an element matters in a multiset. Notation. Set A. The multiplicity of an element is the difference of multiplicities in the given multisets. Set F negative, it's 0. Sum. The multiplicity of an element is the sum of its multiplicities in the given multisets. For example, suppose that P and Q are the multisets of set 4A, 1B, 3C, and set 3A, 4B, 2D, respectively. Find P union Q, P intersect Q, P minus Q, and P plus Q. Solution. We have P union Q equals set max 4, 3, A max 14B max 30C max 02D equals set 4A, 4B, 3C, and 2D. P intersect Q equals set min 43A, min 14B, min 30C, min 02D equals set 3A, 1B, 0C, 0D equals set 3A, 1B. P difference Q equals set max 4 minus 3, 0, A, max 1 minus 4, 0, B, max 3 minus 0, C, max 0 minus 2, 0, D equals set 1A, 0B, 3C, 0D equals set 1A, 3C. P sum Q equals set 4 plus 3A, 1 plus 4B, 3 plus 0C, 0 plus 2D equals set 7A, 5B, 3C, 2D. This example demonstrates how to perform union, intersection, difference, and sum operation on multisets by applying their respective rules for calculating the multiplicities of each element.
And that's the end of our discussion.
Thank you for your time
Listening.
And watching.
Bye!